This is the Economic Club of Florida, a distinguished platform for discussion of the major national issues of the day. On today's program, Greg Boebinger, Director of the National High Magnetic Field Laboratory, on how science turns a profit.
If you think of us as a company, our product is educated people, and our user community published over 400 refereed papers in the literature. Then other people use this information to write the next generation textbooks that then educate the next generation of engineers and technologists who then know how to make something that can turn a profit.
Good day and welcome to the 563rd in our series of distinguished speaker programs. I'm Harvey Bennett for the Economic Club of Florida. We're about to get a gee-whiz glimpse into the future and a lesson on an institution that has a big economic impact here in Tallahassee and the entire state of Florida. Joining us is Greg Boebinger, Director of the National High Magnetic Field Laboratory at Florida State University. I know you don't like to be called doctor, but welcome.
Well, thank you. It's great to be here. I'm looking forward to giving a presentation on the Magnet Lab. We just got our core funding grant renewed for the next 5 years. So we're celebrating. Christmas came early.
Terrific, yes. Terrific. Well, let me ask you the obvious question. Why don't you like to be called Dr. Boebinger? You do have a PhD.
Yes. So I think I just feel like the title builds a wall. And it's already difficult enough to build the links between scientists and the population at large. We speak different languages oftentimes. The population is sometimes, and much of the economy is focused on sort of quarterly returns. We're looking at problems we've been puzzling out since decades. So the time scales are different. There's enough difficulties in making this communications bridge that adding titles just seems to needlessly add one more barrier.
Understood. Good point. So tell me, Greg, what is the MagLab and what fields of science does it impact?
So the MagLab is first and foremost an institution that exists because the largest magnetic fields are a very valuable research tool, but they're too expensive and too complicated to be located in single professors' laboratories. So decades ago, a National Magnet Lab was formed, and in 1990 it came to Florida State University, University of Florida, and Los Alamos National Lab, where we have 3 branches. And we run these magnets that are so much larger than exist elsewhere. They need special expertise and special techniques to run the magnets, but also they need spectacular scientists on board and technicians and supportive staff so that we can host up to 2,000 scientists a year who come here to do their experiments.
And it has the distinction of being the world's largest and most powerful mag lab?
Indeed, yeah. So we get users from all over the world, including from the vicinity of other national magnet labs who can do great experiments at those other facilities, but occasionally they find they need to come to one of our branches because we've got a unique magnet, a unique technique, or a unique talent among our pool of scientists.
Now, I know in the upcoming address to our club, you're going to get into the specific fields of science that your research applies to, so I don't want to spoil that, but let's talk about you. What is your particular specialty, and what's the coolest thing you've ever done or been a part of?
So my specialty is a branch of physics called condensed matter physics, and I sometimes describe that as the physics of things that are on a human scale. So we're not the astrophysicists. We don't study galaxies and stars and the universe itself. We're not the nuclear or high energy physicists that study parts of the atoms and the quarks that make up protons. We study, things that are more on the scale of human life. So from individual cells on up to large, constructs that might be 10 meters, 20 meters. It's science of the human scale, physics of the human scale is the way I describe it.
Very practical.
Yeah, our branch invented the transistor. That's had some impact on society, I think.
I think I've heard of that.
Yes.
Well, we keep hearing that we need to encourage more young people to get into the STEM field, STEM being the acronym for science, technology, engineering, and mathematics. How did a young Greg Boebinger figure out he wanted a life of scientific pursuits?
So the first message I want to get across is that even those who end up in science, like myself, often don't have a straight path. Sometimes I hear people know from a very early age what they want to do. I had no idea. In fact, I would tell adults when they would ask me as a kid what I want to do, I would find the longest word for a profession that I could, or the most crazy out. So for a while I would say veterinarian because it's a long word. Other times I would say a heart surgeon because that would get a big response. I had no idea. I ended up starting in engineering because my older brother was in engineering and he enjoyed it. I found I didn't like it very much at all because I was more interested in where the equations originated rather than how to apply them. So I didn't know at the time that meant I should study physics. And it was a fortuitous summer job out in Tucson where I went to a number of the telescopes in the vicinity of Tucson, Arizona, and started talking to the scientists there. And they said, look, you really should be going into physics, not necessarily astronomy, but some branch of physics. And so I went back to Purdue, my undergraduate institution, after 2 years of having been an engineering and a philosophy major. And they worked very hard to help me add a third degree in physics. So that's how I started in physics. As far as the coolest thing I've been involved in is while I was at Bell Labs for 11 years at the start of my career, my technician and I actually designed, built, and started doing experiments on the world record pulsed magnet at the time, the highest field that had been achieved without blowing something up. And it was clear when this new magnet lab at Florida State University, University of Florida in Los Alamos was funded that I either was going to join that and become part of that team, or I was going to compete and probably get run over because it's clear that's where the momentum was shifting. So we had the world record for maybe a couple years, and I'm pleased to have joined the team that has since blown that old world record out of the water.
Congratulations. Fascinating stuff. We're definitely looking forward to hearing more. Greg Boebinger, director of the National High Magnetic Field Laboratory at Florida State University. Thank you. We look forward to hearing your upcoming address and discussion on the scientific and economic attraction of Florida's MagLab.
Thank you very much.
Now, here's Club Chair Lo Bilby, principal shareholder of Greenberg Traurig, with our formal introduction.
Now for the main event, I'd like to introduce Dr. Greg Boebinger. The National High Magnetic Laboratory, as you all know, is housed within Innovation Park. And it is a national, international success story right here in Tallahassee. The MagLab was founded in 1990 as a partnership among Florida State University, the University of Florida, and the Los Alamos National Laboratory to be operated collaboratively by the three institutions. And I might add, Greg, your website is fantastic. It's very informative, so I advise anyone to go to the website. You will learn a lot, and you'll learn about the different types of magnets et al. Greg is a condensed matter physicist recognized for his research involving high magnetic fields. Greg was born in Cincinnati, Ohio, and grew up in Indianapolis, Indiana. He graduated from Purdue University in 1981 with undergraduate degrees, plural, in physics, electrical engineering, and philosophy. After a year as a Churchill Fellow at Cambridge, Greg then pursued and obtained his PhD in 1986 at MIT. After a year as NATO postdoctoral fellow in Paris, France, Greg accepted a position at Bell Laboratories where he established his own pulsed magnet laboratory and began his research on high-temperature superconductivity. In 1998, Dr. Boebinger moved to the Los Alamos National Laboratory in New Mexico, and he became the director of the Pulsed Magnet Laboratory as part of the National MagLab's Pulsed Field Facility. In 2004, Greg became the director of the National High Magnetic Field Lab here in Tallahassee, our MagLab. He moved to Tallahassee and accepted appointments as professor of physics from both FSU and the University of Florida. Greg is a member of the National Academy of Sciences and the American Academy of Arts and Science. Please welcome Dr. Greg Boebinger.
Thank you. It's a great honor to be here and a great personal pleasure. I was born in Cincinnati, as was mentioned, which means I'm a Buckeye, which means by definition I'm a large hairless nut with little or no commercial value. So I'm not really sure why I'm here, except that the laboratory I run has quite a bit of commercial value. And so my goal in this talk is to present the scientific and economic attraction of Florida's Magnet Lab. And there's some empty seats up front. I tried to design the slides so they'd be visible from the back. We've had a very simple mission since the Magnet Lab was moved down from MIT to this three-institutional partnership. The first is to operate a world-leading high magnetic field user program, and I'll describe what that means, but in a sentence, scientists come here as users of our facilities to get science done that cannot be done anywhere else. We carry out in-house research in support of that user program. One of the aspects of the Magnet Lab that gets a lot of the press are the big magnets, and that's understandable. But it's also the world-class scientists that work at the Magnet Lab that make those magnets so useful, and we attract folks who want to work in this collaborative mode with researchers that come from all over the world. We also, this is a little bit unreliable, but I'm sure I'm going to learn how to use it. Maintain facilities, develop new magnets and scientific instrumentation. We hold quite a few world records, and we conduct education and outreach activities. We are not only a national laboratory, but we are a partnership of these three institutions: Florida State University, University of Florida, and Los Alamos National Laboratory. Excuse me. It seems to record about every other click. Can you go back one?
Yeah, you can back click.
Yeah, in principle, but I'm in practice. There we go. All right. I'm also a little too tall to read the top of my slide. The only facility of its kind in the United States and the largest and highest powered magnet laboratory in the world. This is the center of the world of high magnetic field research. Can you go ahead and advance? I'm getting about 1 out of every 3 clicks. So now there are 4 major MagLab research themes. There's research done in many, many areas, but they can be narrowed down to materials, energy, environment, and life. And many of the world's scientific challenges are too big and too broad for one scientific discipline to solve. And so, advance. This MagLab's interdisciplinary research environment brings together scientists across the spectrum, from physics to engineering to chemistry to biology to biomedicine. And I sometimes joke that part of my job is to try to keep track of what all these researchers are doing so I can run around front and it looks like I'm leading. But these folks from all these disciplines explore fundamental questions about materials, energy, environment, and life with the help of the world's highest magnetic fields. And I'll describe how that happens for each of those areas of research. Next. So, the MagLab attracts researchers from around the world. In 2021, which of course was in the middle of COVID, we still hosted experiments by more than 1,600 users. Our annual number is up around 2,000 when there's not a pandemic, from 159 institutions across the United States. We call this our Delta Airlines map. The lines in red are researchers who went to Los Alamos. Those in purple came to Tallahassee. And those in blue came to our facilities at University of Florida. 3/4 of our researchers come from universities, 18% from government labs, 6% from industry. And if you look worldwide, a total of 279 institutions. This is in a single year. And we're very proud of the fact that there are national magnet labs in Europe, in Japan, and in China, and quite a few of our researchers do research at those labs, but then they need something that we've got, either the magnets, the techniques, or that expertise that I talked about to get that last bit of science. Except for years that contain pandemics, 20% of our users come from outside the United States. In 2021, our program helped to train, and this is what our product is. If you think of us as a company, our product is educated people, so 235 postdocs in 1 year, 508 graduate students, And our user community published over 400 refereed papers in the literature. If you go and look for these papers, they will be completely incomprehensible. I'm going to hammer that throughout my talk. My dad was a minister, and so I was taught to do a lot of this. You won't be able to understand these papers because these are written in the scientific language. But then other people use this information to write the next generation textbooks that then educate the next generation of engineers and technologists who then know how to make something that can turn a profit. And so I like to say that we're laying the foundation for a lot of economic activity, but I'm 5 steps away from making any of that money. And I'm not the expert necessarily on the commercialization, but I have some slides at the end that will give you a sense of the impact the MagLab has. The National MagLab is home to more than a dozen world record magnet systems. And the most important thing to learn is that electricity makes a magnetic field. So what are the requirements to make a MagLab electromagnet? Well, first of all, anytime electrical current is running through a wire, it creates a magnetic field around that wire. So the wiring in your house is creating very small magnetic fields whenever the electricity is flowing. If you coil the wire, then that concentrates the magnetic field in the center of that coil. And that's why many of you in elementary school maybe wrapped a wire around a nail and you attached it to a battery and you made an electromagnet. We're doing the same thing, we're just doing it on steroids. And so the way we do it is we actually build our magnets, and I have 4 of the Florida bitter plates here that we'll distribute. You can have a look. We build our magnets not out of wire because that doesn't handle the forces, as well as building it out of discs. So how do you make a coil of wire out of a disc? Well, to create 1,000,000 times the Earth's magnetic field, which is what we have just over in Innovation Park, you need 30 million watts of electrical power. So when our magnet is turned on, we're consuming about 5% of the total power that runs Tallahassee. We're an unusual customer. We need the electrical current density going through our Florida bitter plates that are being passed around. That is more than 20 times the current density that's in the filament of a 100-watt incandescent light bulb. And you know how hot those get. They're light bulbs because they get so hot that they glow. All right, well, we can't have our magnets be that hot because our 2-ton magnet heats from 40 degrees Fahrenheit to 100 degrees Fahrenheit in about a second after we turn it on. And we would melt the magnet in a few seconds if we didn't have cooling water, which requires more than 2,000 gallons of deionized water to pass through the magnet every minute. Now, people think water conducts electricity. Water doesn't conduct electricity. Water's an insulator if it's deionized. But water dissolves the copper that's in the pipes that it flows through, and it's those copper atoms that conduct the electricity. So we have to continuously scrub our deionized water of copper atoms and all the other atoms that get dissolved into it. And that means that the water that cools our magnets itself, one click, just one, that water itself is corroding the very magnet that it cools. So we're putting these magnets under insane conditions of high electrical voltage, high stresses, I won't go into that, high thermal shock, and the cooling water is like dropping an Alka-Seltzer tablet into a glass of water. It's fizzing away our magnet in real time. We spend over $500,000 just replacing the Florida bitter plates that have been eaten away by that deionized water. Next slide. So how do you make a coil out of plates? Well, you have a plate that that's at the top, and you insulate it except at one location, and then the current circulates around the next plate, and then it touches mechanically the next plate down, light green, then goes to dark green and blue, and then purple. So that's how we stack up these bitter plates and insulators in order to make an incredibly strong coil, in effect, of wire. Next slide. And so we take those discs. This is an exploded view with the insulating plates, but then we crunch them all down, so an actual stack coil looks like this. Next. And then we nest them like a series of Russian dolls. This is an individual bitter plate from each of these stacked coils that then get nested. This is an orange for scale. Next. And then when it's stacked, it looks like this. Each of our magnets has over 20,000 parts in it. And we have a unique design, and this design has been copied by virtually every other magnet lab around the world. This is an improvement over what was up at MIT. It's one of the many major technological advances we've made here since the magnet lab moved to our area. Next. And then that coil has to sit inside this steel housing. So this is about 1.5 meters tall. These are the cooling water pipes, quite a bit of cooling water circulating through. And if the magnetic fields were visible, they would look something like this. And the thing to notice is that they concentrate in the center of the magnet. We're all about concentrating the magnetic field in a small volume, and very little of the magnetic field is outside the magnet. It would be the craziest thing for us to try to do, to build a magnetic field that extends outside where the experiment needs to be done. It's wasted money, it's wasted design. So we are not affecting thunderstorms. We had nothing to do with last night's rain. Next slide. So how big are the Magnet Lab's magnets? Well, I have a chart over here, but let me start with just some numbers. The Earth's field in units of Tesla, which is what we use, is insanely small. It's 0.05 millitesla. There's a whole bunch of zeros in there. The sun's magnetic field, your refrigerator magnet, if you have the old iron oxide magnet, is 0.01 Tesla. Now a lot of you have the more powerful magnets, so instead of holding one snapshot, it can hold up the entire calendar. And that magnet is about 0.3 Tesla, so 30 times stronger. Sunspots concentrate magnetic fields. The junkyard magnet that picks up automobiles is about 1 Tesla. Hospital MRIs are somewhere between 1.5 and 3 Teslas. All clinical MRIs are at about 3 Teslas. So I've graphed those up here, and you can barely see some of the data. So how big are the MagLab's magnets? Next slide. That's how big ours are. And each one of these is a record in the world. So this is the strongest MRI magnet, and I'll show you some data we've taken on rats and mice. It's only this big, so it doesn't fit human beings. But that's the research. We have the strongest continuous field magnet. China just recently tied us with this world record at 45.2 Tesla. This magnet was commissioned in 1999 here. And has done spectacular research. And then our strongest pulse magnet is out at Los Alamos at 101 Tesla. That's the strongest magnetic field that's ever been created without blowing something up. Next slide. So here we have the Guinness Book of World Records award was given to us for this 45 Tesla hybrid. This is a 10-foot high ladder put here for scale. So on this picture, I'm standing about here. This magnet is 30 feet tall. It's the world's largest DC continuous field magnet, which means we can operate it as long as we can pay the electricity bill, which is about $3,000 an hour. Next slide. So the National MagLab is taxpayer funded by the National Science Foundation in the state of Florida, which makes you all stakeholders in our facility. And on behalf of all of us at the Magnet Lab and the scientific community, we thank you for supporting the science and economic opportunities advanced by the Magnet Lab. Next slide. So, superconducting magnets have no friction. They have no need for cooling water. In fact, if you take a loop of a superconductor, and superconductivity is something that comes out of quantum mechanics, I was told there was to be no math, so we won't be digging into the details there. But if you were to make a loop of a superconductor and start an electrical current going, as long as you kept that material cold, and by cold I mean near absolute zero, that electrical current will flow with no friction. It will flow for longer than the age of the universe. So superconductors are a huge frontier for next generation high field magnets. And I'm going to spend some time talking about superconductors, but thank you. Materials, I forgot what the first line was. Materials limit our ability to make powerful superconducting magnets. So the first research I'm going to talk about is research on materials that we then put into magnets. Next. So superconductors are superconductors at very low temperatures, negative 260 degrees Fahrenheit, and they are fueling a revolution in superconducting magnets. As I mentioned, they conduct electricity without friction, but superconductivity is typically very fragile, which is why it's not an everyday phenomenon. It can be destroyed by temperature. Temperatures have to be below minus 440 degrees Fahrenheit. Those are conventional superconductors, but the ones we call high temperature superconductors are because they superconduct all the way up to the warm minus 260 degrees Fahrenheit. So the next goal is room temperature superconductors, which would be 50 degrees Fahrenheit. But we've done pretty well. If you click the next click, just one, absolute zero is minus 460 degrees Fahrenheit. So these only work, the old superconductors, this niobium titanium, which was developed as a technology at Bell Labs in the 1960s and can make magnetic fields of 10 Tesla, and all clinical MRI machines are built with this wire. And then there was a new wire, click again, niobium 310, which is in our MRI for rats and mice, and it goes up in our lab to 21 Tesla. The world record is at 24.6 at a research lab in Japan. But the material is limited not just by temperature, but by magnetic field. So this material only superconducts up to minus 440 degrees Fahrenheit, 10 Kelvin, and 10 Tesla. And then the magnetic field destroys the superconductivity. This material was discovered to go all the way up to the low 20s, and it was the world record for 50 years or so. And electrical current can also destroy the superconductivity. Next click. What we've done is we've built a magnet that has the world record for a superconducting magnet by using these new high-temperature superconductors, because not only do they work at a magnetic a temperature that's well above absolute zero, we're halfway up to 0 Fahrenheit, practically, but it also works well above 30 Tesla, and click, we've built a test coil that's gone to 45.5 Tesla. So research on superconductors to then do development of superconducting magnet technology is one of the big areas of research at the Magnet Lab. Next. So I'm going to talk a little bit about how magnetic fields and electrical currents destroy superconductivity. This is one of the it's a couple slides that are more technical. You can fall asleep for a few slides, but when we get to the easier slides, elbow your neighbor. It'll get a little more conversational after that. But I want to give you a sense of how scientists and engineers have to deal with these limitations. So this is the limit for carrying electrical current, and it's just how many amperes per square millimeter. You don't have to know that. Just how much electricity can you force through the superconductor before it stops superconducting. And this is the limit for surviving in a magnetic field. And the best of the low-temperature superconductors, where you have to be almost at absolute zero, gets killed by a magnetic field of 25 Tesla. And the reason is that superconductivity is an astonishing result from quantum mechanics. It was discovered in 1911. It was not explained theoretically until 1957. One of the three people who teamed up in a collaboration to come up with the theory of superconductivity is Bob Schrieffer, who was a professor here at the Magnet Lab and the Magnet Lab's first chief scientist. And he, as a graduate student, wrote down the key formula that explains superconductivity for the low-temperature superconductors in 1957. Well, superconductivity is like electrons getting together to dance. And electrons have the same electric charge, so ordinarily they repel each other. But under certain conditions, they will pair up. They each have a magnetic field, so one will point up, the other will point down, and then they dance together. And that's the forming of these so-called Cooper pairs that causes superconductivity. Click, next click. If you go to too high a magnetic field or too high an electrical current, you go back to just an ordinary metal, where the individual electrons behave as individuals, they bump into each other, and you can almost understand why a magnetic field would kill this dancing partner if, like two needles of a compass, they're pointing in opposite directions. If you turn on a big magnetic field, they're going to want to line up with the magnetic field. As soon as both of the electrons line up their own magnetic field with the powerful external magnetic field, they're no longer going to dance. And so you have an ordinary metal that carries electricity, but it carries it with friction. And the whole point of superconductivity is there's no friction. Next slide. And this limit is given at a much higher level than I operate at. This is given by the fundamental properties of the material. Nobody knows how to calculate in advance what is the upper critical magnetic field for a material. So the engineers can't work with fixing that. Now, what happens with high temperature superconductors? Click. So this was your niobium curve. These are the high temperature superconductors. Now suddenly they can carry electrical current up to pretty high values at magnetic fields that are well beyond this 25 Tesla. Next slide. And there are several of these high temperature superconductors. Next. 3 different materials that we're studying that seem to be able to remain superconducting and carry good electrical currents up to magnetic fields well above our current world record holder DC magnet. And you may recall we've built a high TC magnet at 32 Tesla. We're now designing one at 40 Tesla. These are not inexpensive magnets. The development and building of a 32 Tesla superconducting magnet, which is a world record holder, was about $16 million. The design of a 40T is going to be about $16 million. The construction will be another $20 million. So these are expensive efforts. How do you use a newly invented material to turn it into a scientific technology? And we're willing to pay top dollar. We're not turning a profit on this. So that next step to economic benefit is yet to be solved. But this is an absolute revolution. Click. And the pure material is only able to carry current down below this graph, down at 1. And here's 10, 100, 1,000. So the material as originally designed was no good for making magnets. Next. But engineers can improve the current carrying capabilities of the wire. And we attracted a group of about a dozen researchers down from Wisconsin in about 2007, the Applied Superconductivity Center, to join us here at Florida State University because they're the geniuses on the materials. We already had the geniuses on the magnet. Let's bring them together and let's control the process from start to finish. And that's what's led to the world record 32 Tesla magnet and the design for a 40 Tesla superconducting magnet. But if you're reading these graphs, who knows, maybe someday we'll be making 100 Tesla out of superconducting magnets and there will be no electricity bill to pay. Next slide. And just to remind you, low temperature superconductors have this barrier that's given by God that just cannot be surpassed. So these high temperature superconductors, when they were invented, have completely revolutionized the opportunities to make next generation magnets using superconductivity. Next. So, research performed using, by scientists using our unique magnets, instrumentation, and expertise. I keep hitting that point. We have to have all 3. There are other magnet labs out there that have great magnets, but they don't have as many in-house scientists, or they don't have as many unique techniques for making scientific measurements. And you can't support just one of the 3 and expect to be as successful as we've been with our magnet lab. So that triumvirate is important. Next. So the last person was the Iceman in 3000 BC, who relied entirely on found materials. His dagger was made of flint. There was reed woven in as a pouch, wooden handle, twine, leather strap, a wooden handle for his axe that was made of copper. Materials initially were found, but at the start of the Bronze Age, new materials were invented. And that's one point I want to get across. You have in your pocket a device that 25 years ago did not, 20 or 2 dozen of the materials in this cell phone did not exist 25 years ago. The one that I point to the most is the touch screen, because it has to be a metal in order to register where you're touching. But look at all the other metals in your life. You can't see through those. They're reflecting. So how do you invent a metal that's transparent? That was just one of the many materials invented to make your cell phone a possibility. Slide. And magnetic fields have helped scientists explore new materials that are the building blocks for the technologies of today as well as tomorrow. Semiconductor industry dramatically relied on research in high magnetic fields. This is what one of the superconductors looks like. The fibers, if you go in and look at a microscopic level, electronics are now flexible. The LEDs were only bright enough for your taillights until the invention of putting some weird elements down at the bottom of the periodic table and mixing those in, and then the LEDs became 4 times brighter. And then after the investment of billions of dollars, probably $10 billion or more, into discovering a blue LED, they then could put a blue LED in front of phosphorus, and so the really bright LEDs that will make you go blind if you look at them, just have a blue LED and a phosphorus in front of it. And when you click them off, that phosphorus slowly decays away. It'll glow for 5 seconds or more. Then the next thing to do was to not make them out of silicon, which is a crystal and can break, make them out of organic materials, because organic molecules, we're soft. We're not crystalline. We're not ceramics. We don't crack when we fall. Well, at my age, you do crack when you fall down. But they're flexible. So let's now make LEDs out of something flexible. Organic LEDs, OLEDs. Now suddenly, you don't have to build single crystals. You can just spin on, like you're doing a painting thing, the organic material, and it'll spread over as big a screen as you want. That's why TVs are so crazy big now. And some of them have curved screens. All of that is inventing new materials. And at the Magnet Lab, there's loads of research now on devices that are 1 atom thick, the smallest devices you can imagine, out of sheets of carbon, graphene you may have heard about, but also the best solar cells out there that outperform what's out in the solar cell farms today are coming from materials that are just 3 atoms thick. And they behave differently when they're thin like that than they do when you make them thicker. Okay. So, modern materials are examples. I really have trouble when I can't see the first word. Many modern materials, I could have done without that one. Many modern materials are example of quantum matter. So when we're inventing materials, we're focusing on what we call quantum matter in many cases. Well, what do we mean by quantum matter? Quantum matter are those materials in which quantum mechanics leads to unexpected emergent properties. Okay, I've just committed the first sin of a dictionary, which is to define something with a term that's not yet defined. Superconductivity is one example of an emergent property. It was a revelation that couldn't be believed at first when in 1911, Kamerlingh Onnes, or more to the point, his graduate student, cooled mercury down to 4 degrees and suddenly the resistance dropped to 0. Surely a wire fell off the sample. They kept repeating it. It kept happening again. And they finally realized something is happening and there's no friction in mercury below 4 degrees Kelvin, 4 degrees above absolute 0. So superconductivity is a surprising, unexpected property that comes out of quantum mechanics. And the point is our ability to calculate even today emergent properties is severely limited. High temperature superconductors were stumbled across. There was not, they had some reasons they were going in the direction they were going, so they were in a deep, dark woods and they wanted to go in that general direction, but they didn't know exactly what they would find. Next slide, next click. So to understand emergent properties, because I don't have time to give a quantum mechanics course, let's pretend that electrons are fish. Next. Emergent properties are not able to be linked to a single fish. You can study everything and know everything about a single fish or a single electron, and you will not understand the collective behavior. You will never be able to predict schooling of fish if you're only studying one fish at a time. And so that's what an emergent property is. It results from collective behavior of large numbers of fish or electrons, and they can be surprising and beautiful, and, click, very important. This is how fish survive by schooling. If fish swam around as individuals, sharks would zoom in on them and catch them. But when they're a school of fish, the shark's attention keeps getting redirected. And so emergent properties are both surprising and beautiful, but they're also very important. And high-temperature superconductivity is still not explained. It was discovered in 1987. Nobel Prize was awarded for the discovery. Whoever explains the theory for why these new classes of materials superconduct at such high temperatures will also win the Nobel Prize. Happens to be the research I'm doing, but I don't think I'm going to win the Nobel Prize. But I'm talking to the Economic Club of Florida. And so, next slide. So, just to remember, one example of an emergent property is superconductivity, and this superconductivity comes about from the pairing of electrons. So instead of everybody milling around at the beginning of this meeting, if instead you were doing a waltz, where everybody's circulating, couples are paired up, that's the kind of collective behavior that the electrons are engaged in. Next. So, why are emergent properties important in quantum materials? Well, for every electron, every new material is a completely new universe. I sometimes make the joke that my astrophysics friends only have one universe to study. Hey, we've got all these materials in which the electrons have different rules. Some of the materials are, atomically thin. The electrons think the whole universe is just two-dimensional, and they behave very differently. So we can go to different materials, and the electrons are experiencing a different universe. Next slide. So if we take two layers of electrons that are sitting on copper atoms, but in this case they can't move around. They're anchored to the copper atom. So they can't move, it's an insulator, but they still pair up. The one magnetic field will be up and the other will be down in this little dumbbell. And in a magnetic field, the pairs behave like a magnetic laser. It's the same math as this laser I'm using to point with, but it transports magnetic fields without friction. Next. So what about a single layer of electrons? We physicists are pretty simple beings. We strip down all the complexities of the chemistry, we pretend it's not important, and we just say, well, let's just make a square array of electrons, and let's have two layers, and let's study what that happens. Then we'll look for another material where there's only one layer, and then nothing was exciting, so we removed some of the electrons, between 10 and 25%, next. And that's high-temperature superconductivity. All the materials, and there are 24 of them, that are high-temperature superconductors, have copper atoms in a square array, and electrons, and you have to remove about 10 to 25% of them, and then you get high-temperature superconductivity. And if any of you can explain that, you'll win the Nobel Prize. Next. Now, why might these be important? Well, if you can transport magnetic fields without friction, you might be able to make a quantum computer someday that would compute well beyond any extension of present-day technology and still save energy. There are possible reduction of electricity waste from high-temperature superconductors. If we could replace these power lines that I call the world's biggest toaster, because they heat up and they waste 10% of the energy generated at the power plant just heating the air, if we could replace them by high-temperature superconductors, we could save 10 to 20% off the cost of electricity. They're already used in powerful magnets. They're already used in wind turbines, these materials. The physicists don't know why they superconduct. The engineers don't care. They're making products out of them. Okay, next slide. So in energy, and here I'll pick up some speed. One example in energy, next, is that we can weigh molecules. We will spray 1 drop of petroleum, which is nature's most complex fluid. It's had more than 80 million years under high pressure and high temperature to do every organic chemistry experiment you could ever imagine. And we spray 1 drop of oil into our magnet, and every molecule orbits at a different speed, and the speed with which it orbits is proportional to its mass. It's like a church picnic. The bigger molecules, the adults, move more slowly. The littler molecules, the kids, run around really fast. And just by measuring the time, we know the mass, next, of more than 100,000 different molecules in a single drop of oil, next. And that means we know every chemical. If you know every chemical contained in petroleum, you can learn how to refine lower-grade crude, next. You can learn what's clogging your pipelines, which allows you to unclog them, and next. You can track the evolution of oil spills in the environment. We're able to tell what a tar ball is. Tar balls were not understood until the Deepwater Horizon spill. They were completely misguided into what we thought was in tar balls. And the MagLab figured out what kind of chemicals are in tar balls. Next. We've done more recent research on asphalt. Asphalt is what's left over. It's the junk at the bottom of the refining tower, and it's perfectly passive. You put it on the roads, and nothing reacts with it. And the reason is because, next, it's thought that the molecules are these huge islands of carbon. These are all carbon rings. And so they're water insoluble. Perfect solution. No. under UV light from the sunlight, the same part of the sunlight spectrum that gives you sunburn. Next. What we discovered at the Magnet Lab is not all of them are these big island insoluble tars, but they're what we call archipelagos, small islands that are linked by single chemical bonds. Here the red lines can be severed by a single particle of light, and they're water soluble. So the roads, we've learned just 3 years ago, are actually leaching toxic chemicals into the environment. So now we've got to study what those chemicals do. Next. If you know every chemical structure before and after exposure to sunlight, you can answer important questions. Next. Like what's getting into the river water. Next. We're doing environmental work. Well, if we can do river water next to a road, why not study the Arctic Ocean? Next. So, if you can identify every compound contained in water, you can answer questions of global importance in a time of climate change. We have a project where we partner with Woods Hole and scientists around the Arctic Ocean to collect river water from the major rivers that feed into the Arctic Ocean. Next. And when permafrost melts during the Arctic summer, we can determine what new is getting into the river water that didn't used to get into the river water before the permafrost was melting. So we'll be able to assess impact on the Arctic Ocean of global warming. Next. As far as life goes, again, we use the magnets, the instrumentation, and the expertise. Next slide. If you do magnetic resonance imaging at higher magnetic fields, you go high definition. You get a sharper image. It's that simple. So this is an entire mouse brain that's been imaged in high definition at the Magnet Lab because we have an MRI magnet for mice that's 10 to 20 times more powerful than the MRI magnets that doctors use. If we could develop high-temperature superconductors to make MRI magnets big enough for humans, then doctors could get much sharper images of what's going on in the body. Next. So we have specialized instrumentation that can image individual cells and the nucleus inside of individual cells. Now, we started with big cells 30 years ago. We did the frog egg, 1 millimeter in diameter. But now the record is a single nerve cell, 10 microns across. That's 1/10 the diameter of a human hair. And we can get an image of that with our MRI magnet because it goes to higher fields. And now you can see why we want to push that superconducting materials technology so the next generation magnets might be able to be applied to MRI, because this crowd probably remembers exploratory surgery. You had a pain in your gut and they couldn't figure out what it was. They would cut you open and explore. And who would have thought that magnets would do away with the need for most every exploratory surgery, and you actually get more information out of MRIs than you do by poking around. Next. So if we have a high field, we can now start to look at things other than hydrogen. All clinical MRIs image hydrogen. We're imaging sodium, so it's a really blurry image. Next. The reason that we want to image things other than hydrogen is you're not just water and fat, which have a lot of hydrogen, so you get great MRIs. Next. If dying cells absorb sodium, we don't know why, but we don't need to know why. Next. So if you give a mouse that has this brain tumor a small taste of a candidate chemotherapy, it's not going to damage its immune system, and, next, less than 4 days later, if the tumor lights up, you know that these tumor cells are going to die if you give more of that chemotherapy. So you've been able to get a clear indication that this chemotherapy treatment will work before you've had to do any damage to the immune system. That's not possible today. They guess which chemotherapy to use. They wait a month to see if the tumor has shrunk because they're looking at hydrogen. Look at sodium, but you need a big magnet to do that. Look at sodium, and you can tell if the tumor cells are starting to absorb that sodium, which means they're going to die. Next slide. My final example merges materials and life, and I'll go really quickly through this because I've been given the buzzer here, and go ahead and click. We make little cells, or little dots of material that show up in an MRI. We put them in stem cells. Next. And we can track as the stem cells go to fight the damage that resulted from a stroke in a living mouse brain. So we can watch stem cells as they go to treat the effects of a stroke. I've got a few slides on economic impact. I should probably go through those, or should I wrap? Okay, thanks. Yeah, once I get started, I feel like I'm my dad saving souls here. A few fun statistics from the MagLab: 25,000 researchers from many countries and states, 72 magnets, 17 world records. Next. All these publications, book chapters, patents. We've had over 116,000 visitors to our open house. We've had 21,500 pizzas eaten, 250,000 cups of coffee, 30 languages spoken at the lab, and 2 weddings held at the Magnet Lab. Next slide. We are the magnetic capital of the world. MagCorp is a new private sector company, spinoff of the Magnet Lab, has signed a deal with FSU to help link the private sector to FSU, to help speed things along. They've already pre-negotiated some of the terms of contracts, and that's been a huge success. We annually create $709 million of economic activity in the U.S., $325 million in Florida, $250 million in Tallahassee alone in economic output annually. The source is down here, the FSU Center for Economical Forecasting. Next. Job creation, 4,500 jobs in the U.S., 2,700 almost in Florida, 2,200 in Tallahassee. Next. And the return on investment. For every dollar invested by the NSF Core Grant, we've generated $6.44 in economic activity in the state of Florida. Thank you. Next slide. So stay connected. You can follow us on the web. Thank you for the kind words about our website. We're on social media. Go back just one. And you can keep up with the latest discoveries, job opportunities. I do want to advertise our next open house post-COVID. We will be holding, knock on wood, the last Saturday of February from 10 o'clock till 3 o'clock. We've had up to 10,000 visitors over 5 hours. You can interact with 100 scientists, ask them any questions you want. Thank you very much for your attention. Sorry,
You're good. Any questions?
What's that?
So he's agreed to take a few questions.
Yeah. I'll stay here till 5 o'clock if you let me.
Because of timing, we'd like to limit the questions to members only, and we have a microphone ready for the first question. Cindy?
This is the first time I've ever asked a question in all these economic. Are you involved at all in research or consulting with the UF proton therapy facilities and proton therapy facilities around the country and the world?
So we're not directly connected to any of the proton therapies, but the magnets that we develop will help in steering those protons in a much more compact way. And so proton therapy now needs a big accelerator. One might imagine in the future a unit that could slide into a standard hospital studio, which would make it much more accessible, much less expensive. So that's a very indirect connection, but no direct connection.
Next question.
Great to have you here, Professor. There was the fusion announcement this past week on energy, and can you explain to us that discovery and how does that correlate with your research?
Sure. So I'm pleased that breakthrough was made possible by the use of magnetic fields. That's what gave that final amplification. One of the private sector initiatives on fusion, not the one that made the news just recently, is Commonwealth Fusion up in Massachusetts. We actually consult with them when they do a test and it doesn't quite work out how they anticipated. They ask us to send some engineers up to help diagnose what happened there. So we are involved with that one aspect. Just one quick sentence on a cautionary note. It's a complex landscape. The milestone was huge. They got more energy out than the laser energy they put in. But if you add the energy that went into powering the lasers, it's a net negative. So they've reached what's called scientific break-even, but not engineering break-even. And then it's still not clear how to get the heat out, which would be necessary for economic break-even. But this is a major step forward.
One more question, Dave.
What will it take to get the MRI from the itty-bitty one for the mouse brain to a big one? Is it just a question of money to make it bigger, or is it, are we missing some science?
So the future is the hardest thing to predict, but it's mostly a materials research that needs to be done. The material, those next generation materials, and I mentioned the MRIs are made with this material that was discovered in the 1960s. It's very stable. The other two materials, including the high temperature superconductors, are less stable. And you've got to have a magnet that is not going to collapse its field when there's a patient in there. Because whereas steady magnetic fields seem to have no impact on the human body, pulsed magnetic fields do. And it can be both negative and positive. I happen to be bipolar. I've actually applied pulsed magnets to my brain. Not personally, I hired a doctor to do it for me. And it lifts depression, and it is astonishingly effective. So I not only, what's that?
Don't try this at home.
Don't try this at home. But they have it here in Tallahassee if you need it. And we've had some very public cases of mental illness leading to tragic results. So, I sometimes joke, I not only, design pulsed magnets and build them and set world records and use them in my research, I apply them to my brain. So,
Thank you very much.
Thank you very much.
You've been listening to Greg Boebinger, Director of the National High Magnetic Field Laboratory, speaking before the Economic Club of Florida on December 15th, 2022 in Tallahassee, Florida. For more information on the MagLab, visit nationalmaglab.org. The Economic Club of Florida promotes interest and enlightenment on important economic, political, and social issues of the day. To learn more, including how to become a member, visit our website at economic-club.com. This program was recorded at the Florida State University Alumni Center in Tallahassee, Florida.